All right.
So you're as smart as you say you are? Or I just think you are? Yeah?
Every once in a while.
So you've always liked physics?
No, actually. When I took it in high school, I liked it. In college, as most people, it was misery taught and not a fun situation. But, that being said, it did give me an empathetic perspective with my students, which is an interesting way to put it. But
I'm a bad professor, but it is pretty fast-paced, so it's hard to grasp.
yeah, I mean, it's an interesting thing because, physics really is, as strange as it is to say, it's the easiest science there is to learn because it's visceral, like we deal with it on a daily basis, and it explains everything that happens in the real world. The problem is that professors are so far removed from that it gets lost in the students. It just becomes esoteric. But I mean, honestly, it's but part of the problem is the way that it's taught is very, very formulaic and mathematical, and there's very little
Conceptual?
Yeah, there's very little touch base with reality.
Oh, I wish I'd have brought it. I had a physics exam. Oh, it is. Tell me if this would be a good physics teacher or not.
So we got. Did you get a formula sheet?
No. Well, we make our own cheat sheet, but
okay.
It's like a note card.
Let's see here.
So the first 10 are conceptual, and the last 10 are mathematics or quantitative. I don't know why I missed the first one. That was BS.
That's not bad. Objects charge, nanocoulombs, electric field, strength, proton magnitude, electron acceleration. That's not a bad one. And the charge, yeah. I mean, it's fairly basic, at least most of it. Well, it's not bad. Yeah, it's really not that bad. It's better than most I've seen. Yeah, it's not bad at all. There's a couple of them in there, which I guess you have to have a couple, but if you have a problem that says, here's the charge, here's the field, what's the force? And that's college algebra, that's not physics, That's
easy.
That's the problem with so many professors is they just get lazy and do that kind of nonsense, or they just make it so ridiculously hard nobody understands.
Yeah.
All right, you ready?
Yes, sir.
All right, so let's do this. Let me kind of set up the kind of fundamentals of physics. I was telling you that physics is like 20% fundamental, 80% application, which ends up being the hardest part for most students. So when it comes to the fundamentals of MCAT physics land, you basically have, you might consider doing this for all of the different topics and subtopics. You kind of have how things move, why things move, and then you have the energy of motion. Now, of course, I'm assuming you're taking comp-based?
Yeah.
Oh, you're not? Oh, that's even better. So one thing that you may or may not have picked up from first semester, hopefully you did, but all of basically MCAT physics is derived from Newtonian physics, right? It's all classical mechanics, all based off of momentum. So, at the end of the day, momentum and thermodynamics are kind of the umbrellas over these three things. And so, from a derivation standpoint, they all kind of work together. But from an algebraic standpoint, when you're not talking calculus, when you're just purely looking at formulas, every single question on the MCAT is only going to ask one of these three things. That's all it is.
Okay.
And there's nothing else. There really is nothing else, unless it's just an algebra question. So, when you're going through all the topics, leaving alone maybe optics, and we'll talk about optics when we get there, right? Mm-hmm. But aside from optics, everything fits into one of these three. So when we start talking about how things move, the physics word for this, of course, is kinematics. We talk about why things move. Mm-hmm. This would be forces and Newton's laws. And then the energy of motion, of course, is just energy. So, you basically are dealing with one of three things. Now, starting off with the how things move, and we're going to go through this quickly, so if you need to slow down, let me know, but I'm assuming you'll probably get most of this. So kinematics, at the very least, on the MCAT, we always are dealing with uniformly accelerated motion because there's no calculus, right? So it's got to have uniform acceleration, which means uniform forces. If there's not a uniform force, you can't do kinematics. We call them big five. I don't care what you call them, but your kinematics equations. So when you're talking, for instance, like springs, right? So when you talk about a spring and kind of this idea that if you stretch it out, it goes one way. If you compress it, it goes the other way. When right there, you see the forces in two directions, so it's not a uniform force. So springs will never ask you how things move, right? They'll never ask you how fast, how far, how much, how long. It can't be asked about calculus.
Okay.
So, when you're talking about how things move, you're usually either talking projectile motion or you're talking about stuff moving through a fluid. Occasionally, you'll be talking about electricity, but really not very often. Okay. And so, that's the reason why we start with kinematics, is the stuff you're more familiar with. But I'm going to assume that you can do all of kinematics without any of my help, unless you tell me otherwise. Cool. Now, as far as the why things move, that's where most of the application comes into play here. So when it comes to forces and Newton's laws. So first off, let's talk Newton's laws. So Newton's 3 laws of motion.
I got them.
Do you remember what they are?
First one is motion, or an object will stay in motion unless acted upon. Second one is all the forces acted on an object that will direct the acceleration depending on direction. And the third one is mathematically it's F21 is equal to F negative 1, 2. Yeah.
All right, cool. So that's exactly right. In fact, the way that you said it leads me to believe you probably know more than most people when they say that stuff. With the reality of the application of the MCAT is Newton's laws of motion come in two flavors. It's either going to be F equals ma, or it's going to be F net equals 0. Right? And that encompasses all of that stuff you just told me, right? So when we talk about F equals ma, if you're dealing with F equals ma, and regardless, you got to draw a force diagram for either one of these, right? When you're talking about F equals ma, this is always going to be used to solve for acceleration, and then in some form or fashion usually ends up being a kinematics problem. If it's not F equals ma, which typically it's not, it's usually F equals 0. With equilibrium problems, you're typically just doing up equals down, or left equals right.
The one thing I did have a problem with, even though we haven't really hit it, but I guess you could say mg as well. When to use negative gravity? So is gravity negative when it opposes the natural direction of movement, or is...
all right. So here's kind of the thing. When we talk about conventions in physics, a Cartesian plane is a very standard convention that a lot of people use. However, the MCAT doesn't typically have a preset convention. So at the end of the day, when it comes to sign convention with vectors, it's more about consistency than it is about having like a set rule. So like, for instance, you can call gravity whatever you want. You can call positive or negative, just as long as whatever you pick, you stick with it.
Okay.
Now, what I would tell you to avoid careless errors would be make initial motion positive. So if it's going up, make up positive. If it starts off going down, make down positive.
Okay.
And the only reason for that is it avoids those negative numbers, which
we don't want.
Is a good spot for careless errors. But yeah, I mean, when it comes to those big 5 formulas in the book, they break it up into like 15 different mini formulas for all these different types of motion. Forget that. Just learn the 5 formulas. They always work. Write the 3 things you know, write the 4th variable trying to figure out. Pick an equation, plug it. It's very, very straightforward.
Yeah.
When you start memorizing all that stuff, just like y is equal to negative 1/2 gt squared or whatever, it's silly. There's no reason to do that. 5 formulas will always work. But yeah, I mean, typically the MCAT's not going to set up a convention. If they're dealing with vectors, they're going to use up, down, left, right terminology as opposed to positive, negative.
All right.
And then scalars, they absolutely will test positive, negative. So that's one that you do want to check. So, this up equals down, left equals right. Depending on how familiar you are with forces and force diagrams, some people have problems with this, a lot of stuff.
Are there angles, a lot of angles, or no? Like F, do you deal with cosine and sine a lot?
Yeah, I mean, it does come up. I mean, with drawing force diagrams, typically what you want to do is you want to draw your force diagram, and I guess I can write this down. So with force diagrams, first step, draw, or at the very least, consider the 8 true forces. That's my own terminology of true forces, but you're basically looking at normal force, gravitational force, frictional force,
tension
force, buoyant force, electrostatic force, magnetic force.
What's the B?
Buoyant.
A buoyant, and what's the big B?
That's magnetic.
Okay.
And then the last one would be restoring force of the spring. So there's no other types of forces. That's all you're going to see. Now, every once in a while, friction is called something different, like a drag force. But those are really the only 8 true types of forces that we have. So you want to draw a force diagram with just these forces. Don't break anything up into vector components.
Okay.
And then step 2 is choose your axes. Most typically for basic vectors, obviously using x and y axis, you just hold it up and then break it down. For inclined planes, you take the axis and you tilt them to the inclined plane. And the only other thing you're ever going to have to do is for circular motion, the axis is constantly moving towards the center is positive. And typically, people look at it a little differently. That's about what it is. So once you choose your axis, then that's when you want to break things into components. So separately break all vectors into components and redraw. So one of the big problems, it's not really a problem, but I think one of the mistakes that physics professors do is they draw these force diagrams where you see something like this, right? And it ends up confusing a lot of people, and you end up accidentally adding vectors and their components together. So typically my suggestion is don't ever put components in the same diagram as your actual vector. Like just separate it and do it all over again.
So I have several boxes or several. Okay.
Right. So like for instance, you have an inclined plane, you have gravity, you have normal force. Let's say you have frictional force as well.
Mm-hmm.
We'll go ahead and draw gravity out by itself, break it down into this and into this, and then redraw the whole thing. It doesn't take long to redraw these. Draw it like that, and that. And then you're never going to get confused, right? And so by breaking each one up separately, it ends up resolving a lot of the math issues like the sines and cosines. It's not as complex looking anymore. So once you break everything up into components and redraw, then for each axis, you either do again f net equals ma or f net equals 0. And again, this is that. If it's accelerating, obviously you're using the first one, but typically it's just left equals right, up equals down. And then solve the problem. Of course, the last step is make sure you're actually solving what it asks you for. So, we see a lot of the Newton's law stuff coming up. And, when it comes to torque and rotational motion, it's the same thing, right? Torque is just a rotational force. So, you're doing torque's equal to I alpha, which is just the same as F equals ma. And then if torque's equal to 0, you just do clockwise equals counterclockwise, right? And then plugging your RF sine theta. So, ultimately, this equilibrium idea, this takes care of most of the math questions on the MCAT. And really, if you know your formulas for the 8 forces, then you should be able to do that. It shouldn't be that big a deal.
Okay.
Now, of course, you're never going to see a problem that has a block on a string, on a spring, and a fluid, rubbing against the surface with charge and a field. It's just not going to happen. You're going to have 2 or 3 types. So when we say draw or consider the 8 true forces, it's kind of like that. If you reset everything, you go through that mental checklist. Well, of course, you're going to be able to cut that corner eventually, right? So ultimately, this is the bare bones of it, but you should be able to cut corners. So then the last part, energy and motion. This is where we're looking at predominantly conservation of energy. So when it first comes to the definition of work, it's actually one of those definitions that most people don't really understand or know. So since we're one-on-one, let me ask you, what is work? What's your kind of idea behind it?
The distance traveled per unit time, or in time.
Okay, so you might make the argument distance over times velocity, right? So give me a little bit more than that.
Just tell me, I don't know.
Okay, no worries. So typically when I ask, what is work, usually the answer I get is a force over distance, like force FD, right? But the problem with this is it's a great formula, but it's a derived formula. It's not the definition. Okay. So, work synonymous with energy. It's all about kinetic energy. It's all about energy and motion, right? So the definition of work is the work energy. Okay, the definition of work is the change in kinetic energy. That's what it means to do work. Infuse the system with kinetic energy. Or negative work, suck kinetic energy out of the system. So, a lot of times they'll ask you for, how fast is something going? Or they'll ask you straight up for the kinetic energy. And, it's one of those logical jumps that a lot of people don't connect this idea. They're actually asking for work. That's all they're doing. So this definition right here, this probably is the second biggest chunk of stuff after this. Up equals down, up equals right. So when you start recognizing that, you start seeing it. Questions that took 3 or 4 minutes to do because you're doing this ridiculous long way. Well, now you can see there's a lot faster way to do it with work, and usually that cuts your time down real fast. Now the other side of energy and motion, of course, is when you do kind of this idea of kinetic energy plus potential energy is equal to kinetic energy plus potential energy, and of course you can throw work inputs and outputs up there. But you have this idea of we'll have all these squared percent GH or something like that. Problem with this here is typically there's this jump that most students have just memorized of, okay, if I drop something off a cliff, mgh equals 1/2 mv squared. But not only that, then they have this memorized even further as v is equal to square root of 2gh, which is a great formula. It's the impact equation, tells you how fast something hits the ground when you drop it, right? Problem with this is, if that's all you have memorized, then you can't tell me how fast the spring's moving, or you can't tell me how fast a charge is moving, or really anything at that point. So as long as you understand what you're doing at the beginning and you don't forget about it, the energy problems typically aren't that bad either. And again, usually energy or how fast something's going. So at the end of the day, as silly as it is, that's the entire MCAT. That's all the physics right there. And I mean, I know that sounds ridiculous, but really you can look at everything and it comes down to these 3 things. Of course, you got to know formulas. And I'm not saying you can do it without formulas, but everything is very, very basic. Now, when it starts coming to subtleties and it starts coming to what are some highly tested things and what are some kind of intricacies of the fundamentals. One of the major ones comes from thermodynamics. So you learn this in biology, it gives free energy, right? Universe is going towards a state of what?
Increased entropy?
Yeah, entropy or disorder or chaos, right? So when you're talking about that on a biology level, you see this just straight up entropy. When you talk about it on a chemistry level, you see it with how fast molecules are moving, or something to that degree. But on a physics level, it's very, very applicable, but it deals with this energy idea. So when you're talking about kinetic versus potential energy, which one's more disordered? Kinetic, right? So thermodynamics tells us that nature, I'm going to use the word nature, but the universe drives towards kinetic energy. So on almost every MCAT, there's a question that says, what happens to the potential energy? Regardless of the situation, whether it's electricity or whether it's a spring or whether it's gravity or whatnot, if you're going to pick an answer that says increased potential energy, you're probably about to pick the wrong answer, right? Nature doesn't ever increase potential energy. That's just not natural. You can always force things to do what they don't want to do. But typically, things are going to fall. They're going to fall down. Talk about charges. They want to be happy just like an object on top of a tower wants to be happy at the ground. So, talk about electrons versus protons. They're happy in different places, but they all still want to be happy. So, you talk about the difference between potential and potential energy. That kind of keys in on that. This idea that the position, the potential, well, the happy place is different, but the potential energy level is still always going to be low. So, you can correlate all of these across the board. And, this is at least the starting place of, if you haven't started considering electricity in these terms, gravity I'm not really worried about. If you haven't started considering fluids in these terms, you probably need to start doing that quickly.
Okay.
Because electricity, and you're probably seeing this right now, same with magnetism. When you learn it, you get so sucked into all of the crazy flux stuff, and all of the, the charge density and these ridiculous terms that you kind of forget what you're doing. You just start plugging in stuff, right?
Yeah.
And so, if you actually look at the MCAT questions, I mean, that test is way harder than the MCAT. I mean, the MCAT's all conceptual questions. Even the math questions are all conceptual. You look at most of the math questions, which is asking you is it bigger, smaller, or equal to something. It's not actually asking you to solve. So, when you go back and review your tests, and you go back and review your workbook passages and stuff, you always want to keep something like this out and be constantly checking back to yourself. If I were to just look at this and make sense of the world, what would I have picked? And what you'll end up seeing is you're going to end up correcting 80% of your answers just by doing that.
Okay.
And it's kind of silly, but it's true. So, that all being said then, when we start applying this stuff, that's in gravity alone, I'm going to leave that alone for a But you look at these 8 different true force types,
Mm-hmm.
and other than gravity, all of these are really electromagnetic forces. Right?
Mm-hmm.
You talk about normal forces as a very microscopic, electrostatic interaction. Same thing with buoyant force. Doesn't necessarily help to think of it that way, but because of that, they're all very, very tied together. Now, more specifically, and I'm not going to stay on these too long because, again, this is more of the basic stuff, but these 2 forces right here are really buoyant forces as well to a certain degree. These are your surface forces.
Mm-hmm.
So surface forces are kind of unique in physics. First, you absolutely have to draw a force diagram, and you can't figure them out. Like, it's impossible.
Mm-hmm.
But even more so, surface forces are always resistive forces. So, you talk about normal force, for instance. And let me ask you, what is normal force? Like, what's your idea of, if you had to explain it to a 10-year-old, what's normal force?
Man, I just know how to draw a force diagram.
Okay, no worries. So, when you talk about normal force, what it truly is just simply a surface pushing on a surface, right? So just a solid object pushing on another solid object.
So it would just be like Newton's third with force of gravity.
Well, yeah, and so it's funny because you talk about, like, I use this example in class where I'll take a piece of paper and I'll say, how do I move this piece of paper? And you push it. Okay, what kind of force is that? Well, 9 times out of 10, the answer is applied force. I'm like, okay, somebody name a force. You say they read, name a force that's not applied. Like, every force is applied. That's the definition of a force, an object applying a push or pull on something else. So, when you talk normal force, yeah, it is. It's Newton's third law. They're all Newton's third law. They're all applied forces, every single one of them. Normal force just is very specifically a perpendicular surface pushing on a surface. And when it comes down to buoyant force, it ends up being exactly the same thing, except rather than a solid object, it's a fluid, right?
Okay.
So buoyant force, very similar to normal force. It's a fluid, normal force. So it's a fluid pushing on the surface. And, truly, don't get me wrong, drawing the normal force of the force diagram is the important part. That's how you solve the questions. So I'm okay with you knowing how to do that. So, very typically, we see, we always see normal force as perpendicular to the surface, but, a lot of times we see normal force point straight up, right? It's resistant to just the surface of the earth. It doesn't have to point straight up. I mean, if I push something against the wall, push out from the wall. Does it have to equal mg?
No.
No, right? I make it push down, I push against the wall, you can do all kinds of things. So when it comes to buoyant force, for some reason there's a disconnect there. Buoyant force is just like normal force. It doesn't have to point straight up. It doesn't have to equal mg. A lot of times it does, just like normal force. But buoyant force, if it's a fluid pushing on a surface, well, I mean, think about situations where a fluid's pushing on something it's not straight up. You use a piece of paper. If you take a piece of paper and blow on it, like this, right? It's a fluid, the air pushing on the surface. Buoyant force is going in that direction, right? Has nothing to do with this buoyancy idea that we have. So, this buoyant, I didn't spell buoyant force right. This buoyant force idea, if you kind of start to really understand it as a normal force, and you understand you got to draw pictures, it makes Archimedes' principle less important, and it makes drawing pictures that much more important. Yeah, a lot easier. And then, of course, we have frictional force, friction being the other surface force. Kinetic friction is a little different. It's always constant. It's just the formula. But when it comes to static friction, I'm going to specifically hone in on static here. It's a variable surface force resisting motion. And really it's sliding, not so much motion, but unless you're talking relativity. I had this stupid question. I think we had multiple choice. We had the similar setup of our tests. And our professor had a question there. It was very simple. It said, kinetic friction points opposite motion, true or false? That's all it was. And of course, everybody picks true. Nobody picked false. And there are examples where kinetic friction can point in the same direction as motion. Like if you put a box in the bed of a truck, and the truck's moving forward, and the box starts sliding back, technically the box is still going forward. It's not as fast as the truck. So kinetic friction in the same direction as moving is just stupid. It's ridiculous. So there's relativity, don't get me wrong. But for the most part, you can consider motion. But this idea of static friction, a lot of times the biggest place that people make mistakes here is they set equal to mu times normal force. And you got to remember, if I have a chair and I push with 1 Newton and it's not moving, what's that pushing back with?
It's equal to the force.
Yeah, just the 1 Newton I'm pushing. If I push with 5, it's pushing back with 5. If I push with 10, it's pushing back with 10. So, if I talk about the formula being this mu times normal force idea, well, the coefficient of friction, that's always determined by surfaces. If I look at the surfaces between the chair and the ground, they haven't changed. It doesn't matter how hard I push it. Normal force is determined by weight in that case. It hasn't changed either. So if I were to solve it out, I'd get one number. But clearly, it could be 1 Newton, 5 Newtons, 10. It could be whatever I push with. So, we know that the max static always has this formula. But, the MCAT says, does the object move? I mean, at most you can have 3 answers. Yes, no, or you can't figure it out. Mm-hmm. So the likelihood of you using this is like almost 0. They're asking more along the lines of having to change the max static. You change the surfaces, you change the force and whatnot. But at the end of the day, you have to draw a force diagram. Once you do, it's not difficult to say 1's equal to 1. That's equal to 0. Up equals down, left equals right. Mm-hmm. But you do have to draw a force diagram. So, I mean, you see the same thing over and over again. Draw your force diagrams. It doesn't sound like I need to convince you of that, but, it is, you want to be careful not to cut the corner too far, right? You always want to draw your force diagrams. And then once you do it, analyze the language of the question. Sometimes the question will say something like, do you have your ICC?
I do.
Awesome. Let's open it up to, page 64.
All right, there.
So, question number 3. You can see the experiment there in figure 1. It's the pulley system, right? Question 3 says, the blocks slide across the tabletop. Total force exerted by the table on the block in each trial is.
You said page 64, right?
64, yeah. Or 63, I'm sorry.
63, that's right.
So question 3 on page 63. Take a second to suck up specifics.
Okay.
So, this is one of those ones that most students will look at it. We're talking about the block that's sitting on the table, right? This one here. Most students look at this and do one of 2 things. They say, okay, the table's pushing up on the block. That's normal force. So it's got to be perpendicular. Right? Second set of students go, okay, the block's sliding across the table, so friction. So it's got to be C, parallel. And rarely do people pick answer choice D. Occasionally, people pick answer choice A, and they say, hey, everything's equal to itself.
But it's sliding. So
and so it's one of these types of questions that you look at, and you're like, okay, this is easy. Maybe it takes 5-10 seconds to answer this. But if you just draw a force diagram, and you get a block sliding across the tabletop, we have, you tell me, what forces do we have?
Force of gravity.
So gravity.
Normal. Friction.
There's a rope on it, so we got tension as well.
Tension, yeah, I can say that.
So when I say analyze the wording of the question and the verbiage, well, now when we look at the question, we can hone in on the force exerted by the table. Well, the table's not exerting all these forces, right? We had to pick which ones the table is exerting and which ones.
The normal and gravity, right?
So gravity is exerted by the Earth.
Okay.
Right. Tension is exerted by the block.
Just the normal.
So normal's one of them.
Or friction.
Friction, right? You can always ask the question, if I get rid of the table, what disappears? But both of those do. And so, this is one of those questions that students usually jump to answer choice B and pick normal force. But the reality is, analyzing the verbiage, you got to take both of those into account. And so it ends up being neither perpendicular nor parallel. You add the 2 together.
Okay, so tell me what you did there.
Yeah, so if the table is exerting both of these forces, the force exerted by the table is the net force by the table. You just add the normal force to the frictional force, and you end up with the force by the table.
Okay.
So it's just like a result. And it's not that even once you draw the force diagram, it doesn't necessarily mean it's easy. But there's no way in the world you would ever pick that unless you draw the force diagram, right? So, these are typically the questions that are going to differentiate and I'm going to use 115 as opposed to crazy numbers, but differentiate the 8s from the 13s, right? And it's the difference between going to med school and not going to med school. And there's silly things. It's stuff that if I sat the 2 people down, one got it right, one got it wrong, and had a 5-minute discussion, they both get it right. But of course, I'm not going to be sitting there with you. So, this is the stuff where, it's going to make or break you. It's all about consistency. So, the end result of kind of this intro stuff is you need to have a regimented way of doing pretty much everything. And you've seen that with Andy. I know how Andy teaches. There is a regimented way of doing biology and doing chemistry. Like you do it the same way every time. Physics even more so because it's so application heavy. it seems like it's completely different every time you see it.
Mm-hmm.
But it's really not. You really need to do it the same way because there's only 3 things that can be tested.
Okay.
Cool. So, that all being said then, let's talk about how to attack a physics passage.
Let's do it.
Cool. How to attack a physics passage. Then we can start talking content. How to attack physics passages. Let me ask you this. When it comes to physics, how do you perceive yourself? Do you feel like you're good at it? Do you feel like you're bad at it? Are you scared of it?
Scared to the point where I suck at it because I'm scared.
Cool. Okay, perfect. So that's the answer we typically get. So here's the thing about MCAT passages. If you had an unlimited amount of time to take the MCAT, you should memorize the passage. You should take it home with you. You should become its best friend. You should intricately know every single detail. Obviously, you don't have an infinite amount of time. So the question then becomes, is it worth it, and what do I need to pull out of it? When it comes to physics, because that mental block exists so strongly in most people, you pretty much always need to read the passage. Not only that, it's application heavy, so you pretty much have to do it anyway. So,
Skim or read?
Is there a difference? I mean, so what do you mean by skim?
Skim, I guess, depending on what you determine is important, you skim and you look for those things and highlight. Read is you read between the important things as well, because it could lead to the small minutia that would be important, maybe.
Okay, so other than if I pull out of it the seeing the details, skimming and reading basically means the same thing. I mean, I'm not talking reading like Harry Potter or Dan Brown or whatever you read, but they basically gave me the same answer for both of them. I mean, you're looking for important things, right? So we say read the passage. I mean, it is the same thing as skimming. The problem with using the word skim is that when people say skim, they look at it and they go, okay, cool, let's go. And that doesn't do anything for anybody, right? So I would more heavily lean towards read than skim, but at the end of the day, they are basically the same thing. Now, it's actively read, so there are things you are looking to pull out. So things to highlight and things to write down. So when it comes to highlighting, anything that's italicized, even though it's italicized, go ahead and highlight it. Anytime you see definitions, along with this is what forces do. Should highlight that. I'll give you an example of this. So if you go to the next page, page 64, look at the passage on the left-hand side. So we got 2 italicized words. We got drag force and lift, right?
Mm-hmm.
So look at those 2 italicized words. And real quickly, read that first paragraph, and you tell me what's important about those 2 forces.
Okay. All right, so I don't know if I highlighted too much or thought I would have highlighted.
No worries. What you got?
So, projectile motion.
Okay.
Downward acceleration due to gravity.
Okay.
Force of air resistance.
Now let me ask you, do you really to highlight downward acceleration due to gravity?
No, I was
okay, cool. Keep going.
Okay. I'm going to erase it just so I know for future
No worries.
Force of air resistance.
Okay.
Resistive force decreases projectile.
Okay.
Horizontal displacement.
Okay.
Directed opposite, or drag force and then directed opposite to velocity.
Cool.
Component force and air perpendicular to drag force.
Cool. So yeah, I mean, you basically hit the major things. So typically when students read this, what they see in the heat of the moment is drag force is opposite velocity, and lift force is perpendicular to drag force. And the 2 things they miss is the 2 things that drag force does. And if you really think about this kind of predictive nature of physics, or this explaining what happens in the world, what a force does is infinitely more important which way it points, right? Mm-hmm. So those 2 specific things that it does, decrease flight time and decrease horizontal range, that's going to be asked. Like if they're going to put that in there, it's going to be asked. And even if it conflicts with maybe something you think you know in physics, they're even more likely to ask that kind of stuff. Mm-hmm. So definitely make sure that you're highlighting what the forces do. That's usually the most important part of the definitions is what they're doing, as opposed to which way they're pointing. And we see the same thing like with optics, like with mirrors and lenses. You think about, you haven't done mirrors and lenses yet, right? Did you have in high school at all? Cool. So when it comes to mirrors and lenses, you can think about them in terms of concavity, convex versus concave. You can also think about it in terms of convergence, converging versus diverging. So without knowing anything about mirrors and lenses, if you had to make a decision on what's more important, the shape, the concavity, or what's going to happen with the light, the convergence, what's probably more important? Second. Yeah, I mean, obviously the second one, right? Yet, when you talk to most students, they think about it in terms of concavity as opposed to convergence, and then they just a bunch of questions. So, constantly have this idea of what forces do, kind of in the back of your head. The third thing you want to highlight then is, I'm going to write it down and kind of explain. You can write what you need. Different experiments or steps. So, if there's different experiments, like we, very, very common, you kind of change the setup a little bit. Typically, what you're looking for is experimental setup. You're looking for what's being measured, and then you're looking for the point of the experiment. Right? So setup, what's being measured, point of the experiment. And usually the point is different than what's being tested, and they're almost always going to ask a question about both of them. So, when you talk about the point, it's just like cars, main idea, right? We're talking about, I might be sliding blocks across the tabletop, and I'm trying to figure out coefficient equation or something like that. So, that's basically half a passage is those three things. When you're talking about steps, you're really just looking for the main idea. So, the easiest one is general electricity, and you've seen these before. When you look at like an RC circuit, right? You're gonna have like 8 switches and 5 capacitors and 3 batteries and all these resistors. Switch S1 open, S2 closed, S3 open, and all that's great and fine and dandy. But at the end of the day, step 1, charge the capacitor. Step 2, discharge the capacitor. So, we're talking about the main idea of these, and there's going to be one sentence that gives you that main idea, and it's going to be tested. And what you want to write down, all given equations. Don't play games with this. I know it might seem like it's a waste of time. Hopefully it doesn't. It's not like they're going to give you 55 equations. The problem that I've seen way, way too often is this stupid MCAT screen. You have this arrow up, this little arrowhead. Students scroll through the passage, and then they scroll it back up, and there are little things right here. And there's an equation it's like right there. And so they're looking constantly, and they can't find the stupid equation. If you just write them down the first time you go through them, then you never have to worry about that. So just write down all your equations. The other thing that you absolutely need to write down are going to be floating numbers with their units. Have you ever heard of floating numbers before?
No, sure.
Okay. So floating numbers, you're a science dude. You've been a science dude probably your whole life. If I give you a passage and ask you to go find a number, you're going to go to the charts, you're going to go to the pictures, you're going to go to the tables. The numbers that you typically are not going to see are going to be like that number right there, or that number right there, or something like that. So floating numbers are numbers in the words. Like all numbers in the words down. If they're going to ask you to do dimensional analysis, it's going to be on a floating number. So, this with units, again, is important only for that reason. Other than that, you don't need to worry about units too terribly much. So you write down all your equations, you write down your floating numbers, you see you're kind of making a very specific formula sheet for this passage. Step 2 then, and this is really the part where we start getting over the mental block, is to ask yourself what topic, or what subtopic either one, did I just read about? So this has to do with kind of the way the human memory works. We're really, really bad as humans, 1, on memory in general, but 2, on associations. Like for instance, if my mom were to be here next time before I'm here, you see her, you're not going to instantly know that's Jameson's mom, right? Even though she looks a lot like me, she's got blonde hair, blue eyes, brown hair, she looks a lot like me. But you just don't make that natural association because you're not looking for it. So, if I had anything to tell you I have a relative coming up here next time, then you have a much better shot of seeing that, right? It's the same kind of idea. Okay. With biology, I can give you some crazy codon throw a bunch of aces at the end of these words, and genetics and all this other stuff. And it's not like it scares you. You just kind of read it and you go, oh, it's biology. It's in chemistry, right? But when it comes to physics, if I throw a wheat stone bridge at you, or I throw some weird term, everybody freaks out. I can't do that. And so it's really crucial to take these esoteric things and turn them into something you've seen before. Okay. So we're talking about what subtopic. This goes to hydrostatics, hydrodynamics, circuits, optics, or whatever the case may be. But once you figure out what topic it is, then for that topic, you need to write down additional applicable equations. I'm going to start by this too, because there is an exception to this. So let me ask you this before your MCAT starts. Do you have a plan for making a formula sheet, or do you have any kind of plan at all, or you just going to kind of go with the flow? It's kind
I was going to make, when I was going through the book, write down every equation that's boxed in green.
Okay.
And then go through it as many times as I can.
Okay.
Kind of implant it, and then test it before the testing starts. I don't know.
No, and real, come to Jesus moment, right? Are you actually going to write a formula sheet down? I'm not saying you have to.
I don't know.
Okay.
I don't know.
So, I definitely have a plan to stick with. Whatever you decide you're going to do, make that decision.
What do you advise?
Well, you have to be able to do a formula sheet. So, for me, I don't do one because I know it so well that it's not necessary. And I don't have the physics mental block anymore. Like, it doesn't, it's not like I have, it's on the tip of my tongue. I don't have that problem. I also don't get anxious with tests. Like, it's just another thing to me. So if you have test anxiety, you should probably do it. Any kind of test anxiety, this gets rid of a lot of it. It's the same thing, It's the same thing with your physics test. Like, do you need the cheat sheet that you make, or could you have taken that test without it?
No, I needed it for it.
Did you need it for it? Okay. So, what that probably means is you don't know your equations as well as you're going to need to know for the MCAT. Let me ask you this. If you knew those equations better, would you still make a cheat sheet? Okay. Then you probably don't need to do a formula sheet for the MCAT. The only problem with the formula sheet is because of the felt tip pen, the nonsense that they have, it takes up like two or three pages.
So, I know, tell me if I'm right, but like you said, F naught equals MA, it relates to everything. You have F equals QE, F equals MG. It's all the same thing, just different letters.
Yes, that's exactly right.
Now, that being said, this semester stuff, I know it better because I have more time, but last semester stuff, like momentum I didn't really like, torque I didn't really like, but I know it's all the same thing, so it's just a matter of understanding the equation. So
and torque is, like torque's a great example of this, that, when I was into all the stupid engineers were building these benches, oh man, look at the torque, and I'm like, what is torque? It's an engineering thing. And this is the mentality problem we have. And then I went to my professor. I was so excited I learned torque when we had it. Well, he teaches it. I don't understand because he didn't teach it. So then I went to office hours. It's the only time I ever went to office hours as a dude. And I went to my professor and I said, okay, I know the formulas. I know R of sine theta. I know alpha. I know Lever arm times force. I know all the formulas. I just don't understand what torque is. He's like, okay, when you apply force a distance from a pivot point. Okay, I get it. It's a radius. Okay. He goes, you can apply it at any given angle theta. I go, okay. He goes, torque equal R of sine theta. I'm like, look, I don't want a formula. I need to know what it is. He goes, okay. Take that force to a perpendicular angle. We call it the lever arm. I'm like, I know. He goes, torque equal lever arm times force. I'm like, okay, stop. He goes, all right, let's try a different way. F equals MA. I'm like, okay, I'm on board. Torque's kind of like that. Torque equal high alpha. And this is the problem with torque. And the problem with a lot of these concepts is all torque is it would be the same as if I did this. As basic as this is, if I tell you I push to the right with a force of F1, and I push to the right with a force of F2, and I push to the left with a force of F3, and I tell you this thing's not moving, what relationship could you set up?
That F12 is proportional to F3?
Yeah, so F1 plus F2, not only proportional, but equal to. It's not accelerated, right? So if I tell you that I have a pole sticking out from a wall or something, hanging on by a thread, right? And I tell you that this thing's not rotating, right? Well, what could you tell me about the net torque, just like you could tell me about the net force over here? What was the net force in this case?
The net force is, I'm drawing blank.
All right, got two options, MA or 0?
0.
0, right? So what can you tell me about the net torque?
0.
0, right? Again, it's this disassociation of these two concepts. It's the same thing, right?
Okay.
So if I tell you that there's a dude hanging on for dear life on the end of this thing, okay, what's causing this thing? And torque equals 0. Just like left equals right. All this is torque in the clockwise direction is equal to torque in the counterclockwise direction, right? Okay, well, what's causing it to want to go clockwise?
The dude hanging.
The dude, his weight. So the weight of the dude. And then if we gave the pole a mass, the weight of the pole, right? Okay, what's causing it to want to go the other way?
The rope.
Rope, tension, So instead of F1 plus F2 equals F3, what can you tell me about the torques?
F of the mass of the pole and the man is equal to the.
Yeah, and specifically because we're talking torque, instead of forces, torques, right?
Okay.
So the torque due to the dude plus the torque due to the pole is equal to the torque due to section. I mean, it's the exact same thing, right?
Did you ever take a picture of that?
No, okay. I mean, isn't that the exact same thing?
Yeah, no, that cleared out basically everything.
The only difference between
That layer.
the only difference is there's an extra step right here where you have to do R of sine theta plus R of sine theta equals R of sine theta. So you plug in the forces, your R is distance from the pivot point to the force, and most thetas are 90 other than this one. I mean, you know, it's not difficult, though. I mean, this shouldn't be taught. This shouldn't be hard to teach. It really shouldn't, right? And so, like, this is the thing, and this is why I say, you know, this equilibrium idea. This is 70% of the questions on the MCAT. That's it right there, right?
Uh-huh.
And it's just, again, when you're going over your tests and going over your passages, ask yourself which one of these three things every question is. It was like that question, torque question, for instance. You should be asking yourself, okay, I know that I don't necessarily get torque, but it's not one of these three things, right?
Mm-hmm.
And so if you can start to see that, you're just doing the same damn thing. Nothing special. So, back to where we were at. I got a weird tangent here. But these algebral equations, the formula sheet, all this kind of stuff. The reason you're doing this and the way that you should memorize. So when we talk about memorizing the formulas in the book, there's 587. Right?
Sweet.
Every single question on the MCAT is worth a grade point, and the algorithm for getting principal is worth a grade point. So the amount that you study to get an A instead of a B in OCHEM, that's how much you should study for every potential question on the MCAT.
Okay.
As ridiculous as that is, right? So, you know, when we have this question of, well, which formula should I memorize? Don't even ask that question, right? All of your formulas, you need to know them all. Now, of course, there's ones that are more important. Of course, half of those 587 are derived formulas. You don't need to memorize. You just know how to derive them. You know these three concepts. Mm-hmm. But the reality is you need to be able to do all of those formulas at some point. Unfortunately, the other thing about the human memory is in your 2 or 3 months that you have, or 1 month, or however long it is, you can't possibly memorize 587. It's impossible. You can't do it. Like, it is humanly impossible. But I can also tell you this. When you read this word right here, for instance, like when you look at this word, at some point, you know, if you have like a super dyslexic 2-year-old, they might go A, P, P, L, I, C, A, P, L, E, like Sesame Street style, right? I mean, do you do that when you look at that word? You see that one, right? Not only that, if I misspelled it, you'd see it right away. Right? So when you think about the equations, think about every equation is kind of like a letter. Kind of like a letter and a half of a bowl. So when you think about hydrostatics, that's one vocabulary word. You might have 8 letters in it. You might have 8 equations, but that's one thing you're memorizing. And so, like, if you're a flashcard kind of guy, then you put all of those equations on one flashcard. If you're a cheat sheet kind of guy, put all of those equations in one group together, box it, and put it in the same part of the paper every single time. Okay. So when you're recalling these additional algebral equations, you're recalling a note card. That's all. Right? You're recalling one box. You're basically recalling one vocabulary word. Mm-hmm. And so, you know, and it's going to look bad. And if you like make a mistake, you're going to see it's misspelled, right? If one equation is wrong, you're going to recognize it right away. So should you make a formula sheet? Well, if you can recognize that it's misspelled, if you will, then you don't need to, because you're going to be able to recall it. All right, so these additional algebral equations, again, this is your entire formula sheet for the passage. Mm-hmm. And then finally, the last step, of course, is going to the questions. And attacking the questions, really, that's the part that is just attack the questions. There's really not a whole lot to it. Obviously, you want to use process of elimination. You want to think conceptually, big picture. When it comes to physics, if you can train yourself to always ask the question, does my answer make sense? You could probably pull a top 30 percentile without really ever doing anything, just asking which answer makes sense. Now, there are some things you might not know if it makes sense, right? If I told you, I asked you what's the magnetic field, you might not know, what's the realistic magnetic field, right? Mm-hmm. But if I tell you I drop something off a 2-story building, how long does it take to hit the ground? You'd be surprised how many students will take 2 years if the math gives it to them. Like, it's just silly that people don't think about what the hell they're doing, right? So always ask yourself, does your answer make sense? And then also, if you can't understand what that means for a particular question, go back to these. Go back to the
Okay, so for these are the 3 bases. So everything revolves around kinematics or uniform acceleration forces, whatever. Mm-hmm. You know your 3 laws. It's either either has acceleration or it's not. There's no acceleration.
Mm-hmm.
And then the energy of motion. Why did you bring all that up again?
So, let me give you an example. And in fact, let me give you all the examples. There's no reason not to give you all of them, right? So that, again, there's a finite number of things that can be tested. So when it comes to energy specifically, you're going to have one of three situations. You're going to either have gravity, you're going to have electricity, or you're going to have springs. Now, there is, again, optics and waves are kind of a different ballgame, so they don't really fit into this stuff right here. Okay, we'll get there, trust me. But when it comes to waves, you don't talk about motion because it's not a particle. I mean, it is a photon, but you don't talk about the momentum of the guy, right? So it's a little bit different way of thinking about it. But as far as the energy is concerned, these are the three basic ones. So when it comes to gravity, you're dropping stuff off a cliff. Typically, there's something there. There, right? So in this particular case, it would, what type of energy is here?
Potential.
Potential is formula?
MGH.
MGH. Of course, what's this?
Is it on the floor?
It's hitting the floor. So we always talk about
kinetic.
Yeah, so kinetic is formula?
1/2 mv squared.
1/2 mv squared. Let's talk electricity. I have in fact, I don't even really need this. We could use an electric field. But it's kind of the same idea. The proton will start here and then it'll start moving, right? So what type of energy is over here?
I would think kinetic because they would repel. Well, I mean, potential, yes. But
so let's put it like this. The universe goes towards a state of disorder or entropy, right? Which is kinetic energy, not potential. Mm-hmm. Think about potential energy. Another way to label it would be instability or unhappiness. Mm-hmm. Where's the unhappy state?
What?
When they're next to each other, right? So this is a super high potential energy state, right? It's very, very unhappy.
I see. Okay.
It's a much happier state and it's in motion.
Okay.
So we talk about being in motion. Well, what's the formula we use for kinetic energy?
1/2 mv.
Same thing, right? There's no difference. But on the other side, what do we use? What's the formula for potential energy? Do you remember?
Negative kinetic energy. Can I say potential? I mean, potential energy is negative kinetic energy. So I just say negative 1/2 mv squared.
Well, okay. I mean, so realistically, yeah, that would eventually be true. I mean, that's what this equal sign is, right? We're setting it equal. But just like we did up here, we have to have a formula for the potential energy. Do you remember the formula for electric potential energy?
I do not.
Okay, no worries. So you're either going to look at QV, or you can also label this as KQQ over R. One of those two, same thing. Q delta phi.
When do you use R squared and when do you use R again? R squared is when, I thought it was between 2 point charges.
So R squared is for forces and fields.
Okay.
Yeah, and R is for potential energy.
Okay.
So yeah, I mean, basically you're doing the same thing. Instead of gravity creating motion, you have this electric potential energy creating motion, right? But you're doing the exact same thing. You're doing potential energy at a point equals kinetic energy at a point.
Okay.
Same thing with springs then. If you have a spring that's completely compressed, then a little bit later, the spring shoots out through this kind of natural length, and then eventually it'll stretch out as well. Well, when it's moving through that natural length, the center, and we'll say that it'll eventually go all the way right here. Okay, well, if it's moving through the center, what type of energy is right here?
Kinetic.
Kinetic, 1/2 mv squared, same thing, right? And then we have the potential energy over here. Have you done some harmonic motion? Yeah.
I hated it, so I have to go.
No worries. Do you remember the formula for potential energy?
No, I don't.
Okay. It's 1/2 kx squared.
Okay. Wow, okay.
And so, I mean, realistically, it's just like this over here. You're doing the same thing. Over and over again, same thing, right? It's what type of potential energy you're dealing with. You're dealing with electric, you're dealing with springs, you're dealing with gravity. Regardless, you set it equal to 1/2 mv squared. It's the only formula we have for kinetic energy. So, again, the energy of motion, this is what we're talking about. The reason we call it energy of motion is this is the important one. It's the happy state. It's the stable state. But it's also the consistent one. It's the one we almost always are solving for V. Cool. That makes sense.
Yeah.
So, the only other way that potential energy comes up would be in a capacitor, which gets a little bit different. Okay, but primarily, this is conservation energy. This is the way you do it. So it's one
Okay.
Cool. All right.
And you're allowed to snap. I take a picture of that.
Yeah, you do. You're not supposed to do that. I take no liability for it. I didn't. All right, now, so you're aware, because you're in electricity right now, let me make sure you know what's on the MCAT, what's not on the MCAT, all right?
Mm-hmm.
So there's no flux on the MCAT.
Mm-hmm.
You don't need to worry about that. There's no surface integrals or anything like that. When it comes to superposition, so did y'all talk that? Okay.
Mm-hmm.
So it's a scary word to a lot of students. Superposition ultimately is just net force. Right? That's all you're looking at. So you just draw force there. It's nothing special.
Mm-hmm.
Usually superposition problems you can do kind of proportionally. So, I always use, and it's a ridiculous example, but humor me. I always use like guys and girls for positive and negative charges.
Mm-hmm.
So, you put a guy and a girl together, they attract, but two guys, I use urinal etiquette for guys, they repel. But, and obviously I know the world works in a lot of different ways. Like, I get this, not always right, just for whatever reason. Mm-hmm. But then I always use the example, like, let's take like the hottest, like, I don't know, super hot, famous female celebrity, right? And I'll get some names. Let's say you pick someone like Scarlett Johansson or whatever. So I pick Scarlett Johansson. So, and then you take like the hottest guy, and I always use me, just but if you put us right next to each other, instant babies, right? If I take Scarlett Johansson and go put her at 7-Eleven, well, it's not instant babies, but pretty fast babies.
Yeah,
right?
yeah.
Now, go put her in Arlington. Realistically, if I know Scarlett Johansson's in Arlington, I'm going to go make that drive and make babies with her.
Yeah.
Yes, absolutely. Yeah, right? Now, let's say I take another female celebrity, maybe not as hot as Scarlett Johansson, although she's my favorite. Let's take Kate Beckinsale. I'm going to put Scarlett Johansson all the way out in Arlington, hottest girl in the world. I'm going to take Kate Beckinsale and put her right here. Who am I going to make babies with?
Scarlett Johansson.
Am I?
I mean, you love her. That's your
Well,
favorite.
let me ask you this.
I don't know how ugly Kate is. I don't know who that is.
Okay, Rihanna, whoever, I don't know, it doesn't matter, whoever you want to pick. This is somebody who's hot, but not as hot as Scarlett Johansson. Right?
Okay.
I mean, it's this idea of, let me put it in real physics terms. There are stars out there that are trillions and quadrillions times bigger than the sun.
Mm-hmm.
Why are we more attracted to the sun?
Because it's closer.
Because it's closer, right? If, whoever Rihanna's here and Scarlett Johansson's all out there, I'm going to make it because Rihanna, because she's here.
Okay.
Does that make sense? This is proximity idea. We see it in the formulas R squared. It's more important. But where this starts to become important conceptually, let's say I were to take the two of them, Rihanna and Scarlett, whatever, and I'm going to stand right in between the two of them. If Scarlett Johansson's the hottest girl in the world, Rihanna's hot but not as hot, and I only think with my penis, who am I going to go to? I'm right in the center. So if I want to have this decision, if I want to make this decision a harder decision, who should I get closer to? Rihanna, right? Eventually there's going to be a point where I go, well, she's hotter, but she's closer, and I don't know, right?
Yeah.
And if you think about that in physics terms, it's F net equals 0, right? And that's all superposition is if I have plus Q, and I have plus 4Q, I say, where do I put an electron so that the net force is equal to 0? Well, you can make this really complicated, but you can also make it really easy. Should I stand closer to Scarlett Johansson or Rihanna?
Scarlett Johansson.
Well, if I stand next to Scarlett Johansson, is that going to make my decision easier or harder? How about this? Free money. $1 million right here, $1 right here. And you're right in between them. Where are you going? $1 million. Take $1 million and go stick it out in Cairo. Put $1 here. Which one are you picking up?
Probably $1.
Yeah, you're not going to fly to Cairo. It's too far away. You're going to get the dollar, right?
20th.
At some point, there's going to be, it's the same decision.
Cairo was your first thought?
I'm
Egyptian, so I was like,
my soon-to-be sister-in-law and brother-in-law, when I get married in May, we were at their house this weekend, and they're going to teach in Cairo. It's something right now. So. But regardless, doesn't matter. It's okay. Maybe you were doing Cairo then, but regardless, you want to put in Alaska. I mean, fuck, it doesn't matter. The idea here is if you go closer to the bigger charge, it just makes the force much bigger over here, and this one's really small, right? Okay. If I want a net force equal to 0, what is net force equal to 0? What does that mean? What's the
there's
basic
no
concept?
acceleration and no movement.
And really,
the
application of it is up equals down, left equals right. Really drive that. If I want right to equal left, well, if I get closer to this, that's never going to happen. This is too strong, right? So if I want to, have this decision of should I get closer to the dollar bill or the $100 million to make the decision the same, well, I've got to get closer to the smaller charge to make that force the same. Does that make sense?
Okay, I like the money.
You kind of say that? Okay, that works then. So you at the very least, conceptually know it's going to go closer to the smaller charge, right?
Mm-hmm.
Now, how much closer? Well, let's see if we can do this without actually plugging numbers in, because let's be honest, 1.6 times 10 to the minus 19, 8.99 times 10, these aren't easy numbers or fun numbers to deal with, right? Mm-hmm. So rather than dealing with those numbers, let's go back to the basic concept. Net force equals 0. What's that mean?
Up equals down, left equals right.
Beautiful. So we're looking at, in this case, force right equals force left. Well, what force is pointing to the right?
The electric force.
So it's an electric force, right? Which one of the two? This is an electron.
It's pointing to the left.
So this one is pulling to the left.
Mm.
This one's tugging on to the right.
Yes.
Right? It's tugging on to the right. So either way, though, you basically have K, Q, big Q times the electron charge over R1 squared is equal to K times this thing, 4Q, times the electron charge over R2 squared. Nothing special, just a formula, right? Not scary. At this point, this is usually when people start plugging stuff in, and you get yourself into mathematical nightmare. Don't plug in. What can we get rid of?
Big K.
Get rid of big K?
R.
Well, R's are going to be there, so remember.
The electron.
Yeah, so just so we remember, this is R1, this is R2. Okay, it's a little different. But we can get rid of the electron at the very least. Okay. Now, in theory, you get rid of the Q2 with the way I've drawn it, but if they gave you numbers, we could just look at this as Q1 and Q2. Okay. But kind of notice what you have here. You have a Q1 over R1 squared is equal to Q2 over R2 squared. Right? Mm-hmm. If I remove this from electricity, if I were just to give this to you as an algebra problem, if I were to tell you I have an equation that says A over B is equal to C, if I increase A, what happens to B?
You mean C?
No, B.
If you increase A, what happens to B will go up too.
It'll go up too. It's directly proportional, right? So if I come over here, and I know that Q increases specifically by a factor of what? 4. So I've increased A, if you will. That means R has to go up as well. Mm-hmm. R squared's got to go up by a factor of 4, so what's R go up by? 4. Well, R squared's got to go up by 4.
So, 16. Am I confused?
You're on the right track. Do this. In fact, let's do it like this. Let's say 4 over 2 squared equals 1. That's true statement, right? That's true. Okay, let's say I increase the top one to 16. What does the bottom one have to go to?
16.
16, so what squared equals 16?
4.
So if I increase the top one by a factor of 4, I increase the bottom one by a factor of 2, right? And you square that.
Okay.
Makes sense?
Yeah.
Okay. It's a much better way of writing it than actually doing the fractions, so you do something like that.
Huh.
Okay. Now, here's the connection. Here's the way you do this and do it fast. And again, this is the difference between the 8s and the 13s, right? If we're increasing R by a factor of 2, we're doubling R basically, right? Well, okay, if it's increasing, which one's bigger, R1 or R2?
If it's increasing, R2.
R2. So we know R2 is twice R1, right? Well, draw it in the picture. And we know the electron's right here. That's number 1 as well. So you know where the electron goes. It goes a third of the way over, right? You don't have to plug any numbers.
Wow.
Makes sense, right?
Yeah.
I mean, and again, this is the, if you can turn it into this kind of algebra, this proportion idea, it makes everything. So it makes so much more sense. It's so much easier. It's just $1 million less $1.
R2 equals 2 R1. There's 2 R1s is where, okay, makes sense.
Cool. It's just a proportion idea. So, long story short, superposition in electricity, while it gets complicated in a class because you're dealing with angles on the MCAT, this is the complexities. Can you make it this? If you can do that, you can get it right quickly, and you're not really doing electricity, you're just saying algebra. That makes sense?
Yeah, no, sweet.
Cool. All right. Otherwise, with electricity, you do need to know capacitors, although they're not putting them in circuits as much. Now they're more asking properties of capacitors.
Mm-hmm.
So, just make sure you know your basic properties. Let me ask you, what does a capacitor do? Since you just did capacitors.
It stores charge energy.
I like that. I like that last word. So when you talk about a capacitor plate, got a plus Q charge, got a minus Q charge.
Mm-hmm.
What's the total charge of a capacitor?
Yeah, like that 0.
0, right?
Mm-hmm.
So they can't store charge. Right? We know they don't store charge.
It's just energy.
They separate it, they arrange it, they store energy.
Mm-hmm.
Now, they also create a uniform electric field. That's the other thing they do, right? So, they store electrical potential energy, and they create uniform electric field. Just make sure you know the formulas.
Mm-hmm.
You have 1/2 CV squared, and then, V equals EV. But, regardless, this stored potential energy, do you know how capacitors are actually used in real life? I know you probably did them in the lab, but you probably didn't know attention to it is. So capacitors, I don't know if you've ever thought about electricity and the craziness of electricity, but when Ben Franklin or whoever was flying his kite with his key, it always bothered me as a kid, how do you take this lightning that's scary as fuck and super powerful and turn it into a fan charge or an iPhone charge or something? How does that happen, right? How do we control this crazy amount of electricity? And the way we do it is capacitors. That's the way we do it. Capacitors are basically shock absorbers for charge. So you put a whole bunch of them in a row, and this huge power plant of electricity comes into your plug socket and hits the first one. It's like, ah! And then the second one's kind of like, ah! And the third one's like, eh. And the last one's like, so, and it slowly leaks the charge out. So these capacitors, they slowly leak charge. So when we talk about a circuit and how to power resistors, which are anything you plug in a wall is a resistor, it just uses energy, right? Mm. If I were to shoot lightning into any appliance that we have, it's going to blow it up, right? So, if I connect a battery to a resistor, it's going to blow it up. We don't connect batteries to resistors. It's just a stupid idea. I know we do it in circuit and we do it in problems, but nobody does that. You don't connect a power plant to your iPhone. It's stupid, right? Yeah. Rather, what we do is we use a capacitor as a middleman, right? So it's like if I owe you money and I give Andy $5 to give to you. Well, Andy's the capacitor, right? Rather than giving it straight to you, I give it to him to give to you. Right? That's what capacitors do. So this stored potential energy idea, that's all it is. It's sitting on the battery's energy, right? The uniform electric field deals with that, but not necessarily in such a obvious fashion. But ultimately, it does end up being the same thing. So as long as you know what capacitors do these two things, you should be fine. They really are kind of weeding them out, though. Circuits in general are kind of getting weeded out of the MCAT. Magnetism as well is kind of getting weeded out of the MCAT. Yeah. So, when it comes to magnets, the amount of stuff you do in college so greatly is so much more than what you ever see in the MCAT. For magnets, you need to know right handle, you need to know the formula, and you need to know they don't do work, and that's all you need to know. It means nothing. So, unfortunately, the stuff you're doing right now, which is not on the MCAT, right? It's a little frustrating, but at the end of the day, it actually does benefit you. So, I'm not going to touch electricity again unless you want me to, mainly because you're doing it right now. Mm-hmm. So everything else that we'll do together then is going to be fluids, it's going to be waves, it's going to be optics, unless you say otherwise.
Fluid, waves, optics?
Yeah, those are typically the three most important. So what I would say, what you probably want to do then is to go through those chapters in your book and start thinking about them in these terms right here.
Okay.
When it comes to fluids, mainly talking about Newton's laws. When it comes to waves and optics, these don't necessarily work. Optics a lot of times is just practicing geometry. Mm-hmm. But the coolest thing about optics, my favorite part about optics, is when it comes to tying physics into the other sciences, because physics is the basis, right? Mm-hmm. It's real easy to kind of see how chemistry is physics. It's a lot harder to see how physics is chemistry. And out of all of the applications, optics really is the most chemistry one, even though it doesn't seem like it really is. You talk about light passing through glass. Well, what it's doing is it's exciting an electron that jumps up and goes down energy levels. You look it up in a book, you can tell me what color it is, right? That's chemistry right there. It's photon emissions. So, when it comes to optics, you kind of see this chemical approach to it so much easier. It makes everything make sense.
So I know we have a session tomorrow.
Yeah.
At 10.
Mm-hmm.
So.
We'll do Springs too. I'll mention who's absolutely Springs as well. Yeah, we did that
one. What do you want me to have done by tomorrow?
It's whatever you're comfortable doing. I want you to read. I want you to make sure you read through those 4 chapters. Okay. especially the fluids, because we're going to do fluids tomorrow.
Mm-hmm.
And then, if you haven't already started doing physics stuff, start doing the first 6 chapters or whatever. That's all the basic stuff. You probably want to look at the electricity stuff just so you get an idea of what's being tested on the MCAT,
Okay.
as opposed to what you're learning.
I looked at electrostatics. I haven't looked at magnetism yet, but
and I wouldn't focus too much energy on it. So when it comes to the top 6 tested topics, fluids, work energy, Newton's laws, waves, simple harmonic motion, and sound and optics, right?
Mm-hmm.
So this is everything we're going to go over. Things you don't see in electricity and magnetism circuits.
that sucks because I like it.
Yeah, I mean, it's a different type of mind that gets electricity. You're in the minority, but it also very well could be how you're being taught electricity. I mean, sometimes if you're taught the other stuff poorly, then
I think it's one of those things. If you're good at it, you like it. If you're not good at it, you don't
absolutely.
like it.
I mean, like circuits like puzzles. Like a lot of people think it's a game. It's fun.
It's fun. Yeah.
I love circuits. I think they're infinitely fun. It's very cathartic for me.
The one thing that I wish my professor would have taught us is the product over sum rule, for resistors.
R1 plus R2.
Because I fucked up on the exam.
You said equal to REQ instead of 1 over?
No,
Or just the math?
I used it for some reason. I stumped thinking it was resistors, but it was capacitors. And I did in parallel, but in capacitors, it's in series, isn't it?
Yeah, and before you leave, let me show you this. So again, this is so from this point forward, and you forget your college class to a degree, I mean, don't forget what you're doing, but from this point forward with MCAT land, think really, and I know it's easy to say, it's a lot harder to actually put in practice, but think about what you're doing. If you were to put capacitors in series versus in parallel, when you fully charge a capacitor, what happens?
It dispenses evenly. Right.
Okay, what else happens? In the whole circuit, what happens?
What do you mean?
Like if I have a battery hooked up to a capacitor. Do you understand how capacitors work first?
Go through it quickly.
Okay, battery, big set of positive charges, big set of negative charges. Mm-hmm. Right? I'm going to talk about it as current as opposed to electrons. It's really electrons. Mm-hmm. Kind of like a frat house and a sorority house. Frat house kicks out a dude. Dude wants to go get himself a sorority house. So he runs around the street. When he gets the capacitor, the road's flooded, he can't get across. So he just gets stuck. He chills. And it kicks out another dude. He chills. And 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 he chills. Right? Other side of the plate. At the beginning of the day, it's neutral. We got everything. Protons and electrons. Positive, negative. But as these positives build up, these positives over here, say, sausage fest, right? They want to get away. They also want to get them some of the sorority house. So they got 2 really good reasons to leave. So if they have 2 good reasons to leave, fast or slow?
Fast.
Very fast. Almost instantly they all go away. So you build this kind of thing up, right? Well, if you do this long enough, this starts to look like a frat house, and that starts to look like a sorority house. I mean, as silly as that is. So if I have a spare little independent dude, and I charge this thing up to the same size as that frat house, or electrically speaking, I charge this up to the voltage of the battery, well, what's he going to do now?
He's going to remain.
He's going to what?
He's going to remain.
Yeah, you don't want to go there, you don't want to go there. He's like, I got a right hand, I'm cool by myself, right? So he just kind of chills there. So fundamental capacitors, when a capacitor is charged to the voltage of a battery, current stops. Right? So positive charge stops moving, you have no current, right? It's like a broken wire, if you will. Nothing's doing anything. So if you look at capacitors in parallel, if I fully charge that capacitor right there, it acts like a broken wire, right? Is it then still possible, if I'm connected to a battery, is it then still possible to fully charge the other capacitor? Do I have a complete loop if this is broken?
Yes.
I do, right? You can do it that way. So when you have capacitors in parallel, you can absolutely maximize both of them. So if you want to know the total capacitance, you add them, because you can make them both max, right? So you just have C1 plus C2 in parallel. Talk about in series, if I max this out and break the wire, can I charge that thing all the way up? It's impossible. You can't charge them up. So you can't just add them together. You can't ever do that, right? So consequently, it ends up being because of math, but you have to do it the opposite way. 1 over C1 plus 1 over C2, right? And it makes sense, right? I mean, it's just, if you think about what you're doing, then all of a sudden it's like, oh, it's not really, I mean, it is the opposite of resistance. Fine, you can memorize that, sure. But, I mean, it actually does make sense how it works, right?
It's not really math, it's more conceptual.
Yeah, it's absolutely conceptual. I mean, that's, again, disconnected physics.
So just think of it like that when I'm studying.
Yes. Now, electricity's an incredibly abstract topic, so it's really important to think conceptually as you go through it. Most of the other stuff you're naturally going to do that,
Mm-hmm.
but you want to even more so bring it back to these then. But you'll see that. You'll see it as you go through. But the other thing that you're going to want to do as you go through all this stuff is, if you go through like the reading stuff and like you're getting it and there's no reason to read it, start doing passages and stuff and bring questions you have. 'Cause,
Okay.
Aside from teaching,
Do you have any ICCs that you recommend me to do?
I can tell you. I can tell you which ones are good, which ones are bad.
Yeah.
So
Like anything that's going to cover the material thing.
yeah. 1, 2. Actually, let me tell you which ones to skip. That'd be a lot easier.
Okay. Let me get to it.
Yeah.
Okay, go ahead.
So don't do number 3. Number 5 is wonky. It's a good one to do with the wordings real.
So do it or don't do it.
I would try it. It's the most similar to an MCAT passage you're going to get. You don't need to do number 6. So skip 6. 7, 8, 9 are 3 of the most important ones. So you absolutely need to do. Those are fluids, though, so you might want to wait to do those. Absolutely do 10 tonight if you can. It'll tell you if you really know electricity. Let's see. You can skip 13. You can skip 15. You can skip 18 and 19. You can skip. All the others would be good ones to do.
Okay.
But if it's something that we're going to cover and we haven't, don't do it tonight.
Okay. So 10 for tonight for sure. If I get the fluid, do 7, 8, 9.
Yeah, do 10 tonight for sure. If you want to try 12 tonight, also it's magnetism. That would be the other one that
Yeah.
kind of test what you're
I'll
doing.
probably go over that tonight too as well.
Yeah. But you'll kind of get an idea when you look through them. Some of them are optics, some of them are fluids.
Yeah, I got lucky to come to Dallas, man. I'm going to go to Austin. If I had been...
Well, it's funny because Austin used to have the best teachers in the country.
What happened?
Some of them retired, and quite frankly, we came up. I mean,
Yeah. Are you on the best
I
teacher now?
be arrogant ass about it, but we're really good at jobs. Like between Andy and me, like we pretty much. I mean, we have people flying from like India and stuff to come to with us.
Seriously?
Yeah. Some of it's frustrating because a lot of times it's not so much India's the problem. Usually we have students come in from like Russia or something like that.
You're joking.
They don't speak the language, and so most of the time.